So chapter 14 deals with acids and bases, and a lot of this is going to follow up with our discussions of equilibrium because many acids and bases reach an equilibrium position. And being able to figure out the equilibrium position is important for determining things like how strong the acid is or how much of it ionizes or its pH or things like that. So this first set of things is going to be some basic terminology. So we want to understand what an acid and base are. There have been a number of theories of acids and bases over the years. The very first was the Arrhenius theory by Svante Arrhenius. And Arrhenius described an acid as something that produced a proton, an H+. All H+ is a hydrogen atom without its electron, so basically a proton, when you put it into an aqueous solution. Or a base was something that had hydroxide ions. Okay, this is very limited because it doesn't account for acids or bases that don't necessarily fit these descriptors, and yet there are many. For example, ammonia. Ammonia is a base. It doesn't produce or contain hydroxide ions. So according to Arrhenius, it wouldn't be considered a base, but we know it is. So Bronsted and Lowry came along a little bit later on, and they redefined acids and bases to be a little bit more specific. An acid was defined as a proton donor. So anything that would donate a proton to something else, donate an H+. And a base was defined as a proton acceptor. Anything that could accept a proton. So that's typically what we use to determine whether or not something is an acid or base. Does it give up a proton or does it take on a proton? Okay, it's more general and it covers more. When you have acids and bases reacting, or you put an acid into water or whatever, you have what are called conjugate acid-base pairs. Okay, and I'll give you an example of what that looks like. So HA is any acid. The H in front indicates that it's an acid. That's the acidic proton, and the A is the anion for that particular acid. So because this equation is written with a double arrow, it's at equilibrium, we can assume that HA is a weak acid. And we'll see what that means in just a little bit, okay? What's happening in this reaction is that HA is giving a proton, giving an H+ to water. Water is taking that H+. Water becomes H3O+. It accepts the proton, becomes H3O+. That's called a hydronium ion. And HA loses a proton, becomes A-. Okay? So according to Bronsted and Lowry's definition, HA is the acid because it gave up the proton. Water is the base because it took the proton. When water took the proton, it became something called a conjugate acid. Water doesn't like to have an extra H+. So it's willing to give it up again. It's willing to give it up to go back to the left. And if water gives up a proton, then it becomes an acid, right? If H3O+ rather gives up a proton, it becomes an acid. And if A- takes that proton, then it becomes a base. So the acid-base pairs, they go together, okay? And they're essentially connected by the transfer of a proton. So, okay, an acid gives it up and the base takes it. The base becomes the conjugate acid. The acid becomes the conjugate base. So essentially it's like a fight over this H+ between two bases, A- and H2O. Okay? Whichever one is stronger takes the proton more frequently or has a greater affinity for it, then that's going to determine the equilibrium position. So if A- has a greater affinity for protons, it likes to hold on to protons more than the reaction equilibrium is going to lie over here to the left because HA is going to form. A- isn't going to want to be by itself. It's going to want to take an H+, and it's going to want to be HA. But if water has a greater affinity for it, then we're going to lie over here to the right because water is going to take the proton and it's going to become H3O+, if that's a stronger attraction. So it depends on what HA is. Depends on what the anion is. Okay. We have something called the acid dissociation constant. And it is nothing more than an equilibrium constant that is specific to acids and bases. Okay, we can write an equilibrium expression where we remove H+ from an acid to form a conjugate base. Okay, so for that the equation that we just had, HA plus water goes to H3O+ plus A-. The Ka expression, the acid dissociation constant, is the concentration of products over concentration of reactants. Okay, H3O+ concentration, A- concentration over HA. Notice that water is missing. Why is water missing from our equilibrium constant expression? Right, because it's a pure liquid. Pure liquids and solids don't show up in your equilibrium constant expression, so water doesn't show up. Now, H3O+ is the hydronium ion, and that's what actually exists when water takes a proton. But it's sometimes easier to represent that as just H+, because we can't really have protons by themselves just sitting there. They have to be attached to something. They're very unstable. So they'll attach themselves to a water molecule, for example, to become more stable. But really, if you have a certain number of H3O+ ions being formed, you have the same number of H+ ions in solution, and they're just attached to each water molecule. So sometimes it's more convenient for certain calculations to just replace the H3O+ by H+. Okay? So here's a little schematic or diagram of what this might look like, where the water is the little red and white one, and the HA, whatever that is the green and white, and the H part is the white. Okay, and so we get water over here with 3 protons attached to it, and we get the A- by itself. Okay. Acid strength, how strong an acid is not the concentration of the acid. It has nothing to do with concentration. What it has to do is the equilibrium position of the acid's dissociation reaction. Okay, so if you have a strong acid is defined as an acid that almost completely dissociates. In other words, all of its H+ are given to water. And that means that the equilibrium position of this acid's dissociation lies very, very far to the right. Almost all of it dissociates. And since our Ka value is product concentration over reactant concentration, and all of our acid is essentially turning into products, then our value for Ka should be very high, should be very large. So strong acids have very large Ka values. The conjugate base that's created, so the conjugate base is what's left of the acid after it gives up its proton. That conjugate base is going to be very weak, because if a strong acid is really willing to give up a proton, then what's left when it's done isn't really willing to take the proton back. So it's a weak conjugate base. So strong acids produce weak conjugate bases, and they have very large Ka values. It's the opposite for weak acids. Okay, a weak acid doesn't like to give up its proton very much. It likes to hold on to it, which means the equilibrium is going to lie pretty far to the left. Almost all of the HA, the acid, stays together. Very little of it dissociates. Okay, again, for the reasons that we talked about just a minute ago, that means that the Ka value should be very, very small for a weak acid. And that means that the conjugate base that's created should be very strong, because it wants to take the proton to become the acid again. If the acid is weak, it's less likely to lose the proton. So the base that's created is very strong. So in general, the relative acid strengths and relative conjugate base strengths are opposites. Okay, so the stronger the acid, the more dissociation you have, the less likely that the conjugate base is to take the proton to go back, which means it's a weak conjugate base. Weaker acids don't want to dissociate, so if they do, the base that's produced, the A-, wants to take a proton back. It becomes a very good proton acceptor, in other words, a strong base. Here's some Ka values for common monoprotic acids, and you can see at the top we have like the hydrogen sulfate ion or chlorous acid, which have small values for Ka, but much larger than something down like phenol. Phenol is not very acidic at all. It's a very, very weak acid because it's got a very, very small Ka value. That means getting rid of that H in front is very difficult. It doesn't want to happen. Okay. Now, if you have a strong acid, then water is a stronger base than the conjugate base that's produced. Water would rather have the proton than that base would for strong acids. Okay, but for a weak acid, water isn't strong enough to take the proton away from a weak acid, and so the conjugate base of a weak acid is much stronger than water as far as taking a proton, and vice versa with conjugate acids. Okay, so a strong base wants to accept a proton, it wants to take a proton, which means that it's not going to be as good at giving it up. It's not going to be a stronger acid. Water is better at giving up a proton than those, but water is not quite as good as giving up a proton if you have the conjugate acid of a weak base. A weak base doesn't really want to take a proton, so its conjugate acid really wants to give it up, and water would be a stronger acid than that. It would be more willing. Okay. Different types of acids. We have a diprotic acid, and di means 2. Okay, prot means proton, so diprotic means an acid with 2 acidic protons, like H2CO3, H2SO4. Most acids are oxyacids, so HNO3. If you do the Lewis structure of HNO3, you'll see that that H is actually attached to one of the oxygens, and that's the case for oxyacids. Okay, the acidic proton is attached to an oxygen. That weakens the bond because of electronegativity. That weakens the bond between the oxygen and the hydrogen and makes it likely to come off. The hydrogen is an H+. Okay, and then we have organic acids. Organic acids always have the classic COOH, which is called a carboxyl group at the end, and they're very weak. Okay. And then we have hydrohalic acids, which are hydrogen plus a halogen. So HBr, HCl, HF, HI. Okay. Water does something interesting when it's just by itself. As it turns out, water will exchange a proton among two water molecules. So one of them would give up the proton, that makes it an acid. The other one will take it, that makes it a base. So water is both an acid and a base. We have a word for that. It's called amphoteric. Anything that is both an acid and a base is amphoteric. Another word that means something similar, water can both donate a proton and accept a proton, which means it's amphiprotic. So ampho and amphi are prefixes that mean both. Okay, amphoteric means it's both an acid and a base. Amphiprotic means it both donates and accepts protons. They sound like they're the same thing, but they're not entirely the same thing. One is very specific to the Bronsted-Lowry definition. Okay. If I have that situation, then I can write an equilibrium expression, concentration of H3O plus times the concentration of OH minus, or just the concentration of H plus times the concentration of OH minus. Water does not appear in that expression because it's a pure liquid, so there's nothing in the reactants that will show up in my expression. Now it happens that this is called the dissociation constant for water. It's a very special equilibrium constant because it's very specific to water only. And at 25 degrees Celsius, the concentration of H plus and OH minus are equal in pure water, because for every one molecule that gives up a proton, one molecule takes a proton. So you're going to produce as many of each of those ions. And at 25 C, the concentration is 1.0 times 10 to the minus 7. Very small. So water is really, it's so weak that you can't even register it as an acid or a base. Okay. But if I put those concentrations back into my expression for Kw, then I find that the value of Kw at 25 C is 1.0 times 10 to the minus 14th. And that's an important number. Okay? So water autoionizes, it self-ionizes. That number, 1.0 times 10 to the minus 14th, helped us to develop the pH scale. Okay. The pH scale is a more convenient way than using concentrations, because concentrations are usually going to be very small, very large numbers. They're harder to work with. The pH scale is generally right from 0 to 14. And it's calculated. Anytime you see a lowercase p in front of something, it means take the negative log of that thing. And so pH means take the negative log of the H plus concentration. This is why sometimes we just use H plus instead of H3O plus. Okay. When you're trying to figure out how many decimal places to have in your pH or in your log, the number of decimal places in the log, in the pH, is equal to the number of significant figures in the original concentration. So if you had a concentration of 1.00, that is 3 sig figs. When you take the negative log of that, your answer should have 3 decimal places. That's just how that works, okay? As the H plus concentration goes up, since it's negative logarithm, the pH goes down. So the higher the H plus concentration, the lower the pH. Think about it. Acids produce lots of H plus. Acids have low pHs. Okay. The total of the maximum value of pH is 14. You can also find the negative log of OH minus concentration. That would be called POH. And as it happens, pH and POH together add to 14. They're complementary. Okay. So here's a little pH scale. The value of H plus concentration, you can estimate the pH based on the exponent. Okay, so if you take the negative, and it's base 10 logs, right? So if you have a solution whose concentration of H plus is 10, something times 10 to the minus 10th, then its pH is going to be about 10. And the coefficient, of course, will change that a little bit. You can just calculate it. But if you have to estimate, that's how you do it. Anything above 7 is basic. Anything below 7 is acidic, and 7 itself is considered neutral. The concentration of H plus and OH minus are equal, therefore it's neither acidic nor basic. And these are just some common substances in their pH.